Hello everyone, and welcome to a little summary, if you will, of what we saw in the one-dimensional projectile motion activity that you just did. So this is really, we're going to look at the very last one, the third part of the activity here, where you threw the ball from the ground up towards the motion detector, and then it fell back down again. So you let it go up and come back down. Your graphs hopefully looked something like this. Now watch that again. And a couple of things about the graphs. First of all, notice that it's below the time axis on a position time graph, and that's because the motion detector thinks of itself as zero position. And so you're always under zero, right? You're below zero, which makes it negative. Right? So you're far away, and then you're getting closer to the motion detector, and then further away again. Remember that this dotted line here represents the highest position of the ball. If you watch it again, right when it gets to the highest point, that's when it crosses that dotted line. The velocity time graph, we have a positive decreasing velocity because it's slowing down as it goes up. At the highest point, it's zero velocity, but it doesn't stay that way. It then begins to fall down and speed up in the negative direction. And notice the slope of this graph, of the velocity time graph, which is the acceleration, is constant and negative. So we have a constant negative acceleration. Now, what would the motion map look like in this case? Well, I'm going to actually do this in real time here so you can see this motion map be made, and then we'll talk a little bit about why it looks the way it does. And this might be an opportunity for you to actually compare this one to the one that you have on your sheet. So here we go. You ready? So watch that again. Way up, highest point, way down. Okay. So a couple of things I want you to remember here. First of all, the dots are position dots at equal intervals of time, right? Equal amounts of time between any two dots. The red arrows are velocity arrows. Notice they point up as it goes up. They point down when it comes back down. And these arrows are the acceleration arrows. Notice that they are all the same size because it's uniformly accelerating, and they're always pointing down because the acceleration was always pointed down, was always negative. Now, a couple of things that you should notice here about this motion. Let's look at it on the way up. On the way up, several things are happening. The dots are getting closer together. The velocity arrows are getting shorter and shorter. And notice that the acceleration arrows point in a direction opposite the direction it's moving. It's going up, but it's accelerating down. All three of those things should lead you to think of it as slowing down, right? Those all are things that happen when an object is slowing down. Dots get closer together, velocity arrows get shorter, and the acceleration points in the opposite direction it's moving. The highest point here is kind of interesting because at the highest point, the velocity is instantaneously zero. It's at rest. Okay? However, so that's why there's no velocity arrow here. However, it doesn't stay at rest. It doesn't get stuck up there at the highest point. It comes back down. So it is accelerating. Okay? It is accelerating, and that may seem a little strange. It's not moving, but it is accelerating. Well, a couple of ways to look at this. First of all, think of this from a force perspective. Since this is projectile motion, gravity is acting on the ball all the way up at the highest point and all the way down. And gravity is the only force acting on the ball. So therefore, at the highest point, there is a net force acting on it. That force is gravity. And therefore, it is accelerating. Net force is mass times acceleration, Newton's second law. From a motion perspective, it also has to be accelerating. It is doing something special at that highest point. Look what it's doing just before. It's going up. Look what it's doing just after. It's going down. So what is it doing at that highest point? It is actually changing direction. And anyway, if it wasn't, if you thought, hey, it's not moving, so therefore it's not accelerating, well, then what would happen to it? Something that doesn't move and doesn't accelerate doesn't go anywhere. And when you throw something up in the air, it doesn't get to the highest point and stick there and hover, and it comes right back down. And so it is accelerating at this highest point. That's why there's an acceleration arrow, even though it's at rest. On the way down, on the other hand, the dots get further and further apart. The velocity arrows get longer and longer, and the acceleration is pointing down the same direction it's moving. All three of those are indicative of something that is speeding up. Dots get further apart, velocity arrows get longer, acceleration points in the same direction it's moving. Hopefully you see this as an analogy of the cart going up and down a hill that we did in the speeding up and slowing down activity earlier. It's really actually the way that Galileo studied projectile motion in one dimension. He actually put it and decided it was the same kind of motion as a ball would be on an incline. And so he looked at the ball on the incline and said, this is the same thing that's going to happen for free fall. Now, a couple of other things that may or may not be in the one that you drew. I want you to notice here that there's some beautiful symmetry going on here. Right? There's some beautiful symmetry in the original graphs, and there's some symmetry here in the motion map. Now, why is there some symmetry? Well, again, from a force perspective, the only force acting is gravity. And as long as we're near the surface of the Earth, the force of gravity, the weight of the ball, is constant. So if we have a constant net force, we get a uniform acceleration, which means that on the way up, it slows down just as fast as it speeds up on the way down. You say that again, since the acceleration is uniform, it will slow down on the way up just as quickly as it speeds up on the way down. And therefore, we get this beautiful symmetry. Now, that's represented two different ways here in our motion map. Take a look at the position dots. Right? Notice that the corresponding position dots are exactly the same height. See the ones there? It is speeding up just as quickly as it's slowing down. The other one is perhaps even a little more subtle. Look at these velocity arrows on the way down. Now, first thing you might notice is that this is one of the few times when I haven't just drawn them to fill in the space between the two dots like I did on the way up. That's because I knew there was some symmetry going on. Well, if it's speeding up on the way down just as quickly as it's slowing down on the way up, then at this height, it should have the same speed as it did at this height, just in the opposite direction. So, the velocity arrows at corresponding positions are the same size, same speed, if you will, just in the opposite direction. So you look at those again. Right? See, those two arrows are the same length, those two arrows are the same length, and those two arrows are the same length. So once again, you might want to check yours and fix it if it doesn't have all of these fine little points that we want to look at one-dimensional projectile motion. Now, let's take a look at this projectile motion. Some of the things that we just talked about here about it. Okay, let's look at this from a force perspective. First of all, we know the projectile motion means that the only force acting on it is gravity. Right? There's no air resistance, or as in the lab, we can neglect the air resistance for the most part. That means that our force diagram is pretty straightforward. All we have is the force of gravity. And this is the force diagram as it goes up. This is the force diagram at the highest point, and this is the force diagram on the way down. They're all the same, right? All the same force acting. That means from Newton's second law that the net vertical force has to equal the mass times the acceleration. Remember, this is just a fancy way of saying net vertical force. That is the vector sum of the vertical forces. Summation sign, right? Vector sum of the vertical forces, which is a fancy way of writing vertical net force. Well, the only force is gravity, and it's down, which makes it negative. Notice I took the arrow off because I put the direction in. Now, as we've done many, many times so far this year, we can rewrite gravity in a more fundamental way. The force of gravity, or weight, can be written as mass times gravitational field strength. And once you substitute that in, notice something special that happens here. If we had a bigger mass ball, let's say we used a shot put instead of the soccer ball, it would have more mass, which means it would weigh more. There'd be a bigger force of gravity trying to accelerate it. But at the same time, there's also more mass, which is a measure of the object's inertia. Right? There's a greater resistance to changes in its motion. And therefore, these two things will cancel out of the equation. That's a really deep idea. As I've mentioned before, it's the jumping off point for Einstein's general theory of relativity. But mathematically, it just cancels out. But again, more mass means a greater force of gravity accelerating, trying to accelerate the ball. But more mass also means more inertia, more resistance to changes in its motion. And those two things proportionally cancel out of the equation. So our acceleration just becomes negative g. And after doing the labs that we've done in here, we know that near the surface of the Earth, our gravitational field strength is 9.8 newtons per kilogram. Now that may not look like an acceleration to you, units of newtons per kilogram, but remember here, a newton is a kilogram meter per second squared. That's what we defined a newton to be. Remember, it's the force required to make a 1 kilogram object accelerate at 1 meter per second squared. So the kilograms cancel, and we're left with units of meters per second squared. So these are acceleration units, just not written that way. Right? So if we put in the substitution of the acceleration units, we can see that the vertical acceleration is negative g, which is negative 9.8 meters per second squared. The negative is because it's going down. Right? And down in a conventional coordinate system is negative. Notice something about this. There's no time factor here. It's the same on the way up as it is at the highest point as it is on the way down because the forces are the same. There's only the same force of gravity. That means that this is a uniformly accelerated motion, as we saw on the graphs. And we know a lot about uniformly accelerated motion, right? Including a beautiful set of 4 kinematic equations that we can use to model this uniformly accelerated motion. Now, you'll notice several things that I've changed about these compared to the original ones we had when we were talking about horizontal. First of all, I changed all the x's to y's. So this is now vertical displacement, final minus initial vertical position. Y means vertical position, x means horizontal position, z means in and out, right? So y minus y sub o is final minus initial vertical position or vertical displacement. I've replaced all of the a's for acceleration with g's because we know that the acceleration is our old friend, the free fall acceleration near the surface of the Earth, negative 9.8 meters per second squared. That's just a given. Right? When we do problems, and you'll see in the next video on an example of this, that it's just something that you have to read right into the problem. Okay? So it's a special acceleration. The other thing I did here really isn't that useful in one dimension, but we're eventually going to study two-dimensional projectile motion, and we're going to have to distinguish between the vertical part of the motion and the horizontal part of the motion. So this is vertical. So notice here I've added little y subscripts to the v's. That's to tell you that these are vertical velocities. So this is final vertical velocity. This is initial vertical velocity. VOY stands for the initial vertical velocity. So again, 3 things that I've switched around here. I've changed the horizontal position symbols to vertical positions, so Y's. I've changed the acceleration to free fall acceleration, G. And I've added these little Y's in for right now, just as practice, because it's vertical, so that we recognize that everything we're talking about here is vertical. We've got to be really careful in these problems, too, about the negative signs. There's lots of negatives in projectile motion because lots of things are pointing or moving downward. So I hope you've enjoyed this little summary of our one-dimensional projectile motion activity.